Okay, in this video we are looking at timber columns. So we have looked at the design and analysis of steel columns, and now we're going to look at timber columns. And unfortunately, because timber is just such a wildly different material than steel, the analysis and design procedures are wildly different as well. So the thing about timber is because it's a natural occurring material, it's much less predictable in the way that it behaves, and so we have to be more conservative in its design. So with steel columns, we were able to calculate the load that would cause buckling to occur using the equation developed by Leonhard Euler. So we were able to find Euler's load or Euler's stress that would cause buckling. Unfortunately, wood doesn't behave predictably enough for these equations to apply. There's all sorts of natural defects that can occur in wood, so we have to take a more conservative approach. We still want to make sure that our column is not too slender so that it doesn't buckle, and so we do need, with wood, regardless of the size of the column, we need to make sure that this variable L sub e, which we'll define here in just a moment, is less, L sub e over d is less than or equal to 50. Okay, so we never want this effective length, which is what L sub e is, effective length divided by d, which is the least dimension, to be less than, we always want it to be less than or equal to 50. We never want that to exceed 50. So L sub e is the effective length, and this is actually the same with steel, this definition of effective length. Effective length is equal to K times L. So we are using the same K values depending on the support conditions of the column. So the most common of which is pinned, in which K is equal to 1. But we could also have fixed pinned, or fixed or fixed free. So depending on what the support conditions are, we'll have our K multiplied by L, which is the unbraced length. We typically look at columns that are unbraced. They're only braced at their supports at either end, at the bottom and the top. So the unbraced length is the length of the column itself, multiplied by K. That's the effective length, which we call L sub E in timber design. D is the least cross-sectional dimension. So if we were to look at a cylindrical post, like a telephone pole, D would just simply be the diameter of the circle. So in that case, D would just be equal to the diameter. But what about a square? If we have a square column, D is just going to be the width or the height, because in a column, in a square shape, the width and the height are the same. If we were to use a rectangle as a column, like a stud in a building, the D width would not be the width from side to side as I've drawn it here, but the shorter of the two dimensions. That would be D. So what we can observe from this is that the strength of the column is somewhat limited by the least of the two dimensions. So making a rectangular column, choosing a rectangular column, although it does provide us some additional area, which will slightly increase the strength of the column, it doesn't really increase the resistance to buckling. So the most efficient shape for a column is going to be either square or circular or some other, I mean, those are really the primary two. We don't have too many regular polygon shapes like pentagons, but those would be the best, most efficient shapes for a column. A long, skinny rectangle will provide us a slight amount of strength, but really it won't be much more efficient than a square with the same D. Okay, so that's the very first step. We want to make sure that effective length divided by D does not exceed 50. Once that is established, we simply need to see about the allowable stress. The allowable stress for a timber column is equal to F sub C multiplied by C sub P. This comes from the appendix. It is the allowable stress in compression, that's what the C comes from, parallel to the grain. And that's how timber beams are arranged. We've got, not beams, columns. A timber column runs the same length as the trunk of the tree, so the grains of the wood are running vertically. So when we apply a load to a column, that load is running parallel to the grain. And I just looked this up to verify it. It is Appendix F in the book. Provides allowable compressive stresses for a few different species. We got Douglas fir, southern pine, hemfir, eastern white pine, and redwood. So depending on what species you're using, make sure you're using the proper allowable stress parallel to the grain. Now, it's not just that. We're also taking that value and we're multiplying it by this C sub P, which is a stability adjustment factor. So basically, the stability adjustment factor is based on how slender the column is. A very tall, skinny, for lack of a better word, a column is going to have a smaller stability adjustment factor. We're going to have to reduce this allowable stress. If we have a relatively short and stout column that is not likely to buckle, then the C sub P value is going to be somewhat close to 1. We can basically take the full allowable stress. So this is just one adjustment factor. In the actual code for designing timber, there are many adjustment factors for things like temperature and humidity, and whether it's a single column or a repeated element like a stud, and many others that I'm not remembering off the top of my head right now. So it all, again, comes down to the fact that the behavior of wood. It's a natural material. It is affected by humidity. It has all sorts of natural defects, knots and splits and checks and twisting. And so we need to account for all of these variables in a timber column. And so they're in an actual code-approved design would have many of these adjustment factors. In this class, we're just looking at this one, C sub P, the stability adjustment factor. So we need to calculate the stability adjustment factor. It's not something we can just look up. And it's kind of a complicated equation. So the stability adjustment factor is equal to 1 plus alpha divided by 1.6 minus the square root of 1 plus alpha divided by 1.6 squared minus alpha over 0.8. So that in and of itself is a somewhat tricky algebraic formula. It's going to test your knowledge of order of operations and punching buttons into your calculator. I typically recommend that students break this down into smaller parts. For instance, calculate this part of it separately, write it down, calculate, either everything under the radical separately, or you could even break it down into this part and write them down separately, then find their difference, then take the square root, then subtract that from this value here. So just make sure you're following order of operations and using all the necessary parentheses. And you may notice that this equation has this alpha variable in it. We haven't talked about alpha yet. What is it? Well, it's a variable that, again, needs to be calculated. It's going to be 0.3 times E, the modulus of elasticity, divided by our effective length, divided by D, LE over D, which we need to be less than 50. We're going to square that and then multiply it by the allowable stress in compression parallel to the grain. So this gives us alpha. Alpha goes into the stability adjustment factor formula. We take the stability adjustment factor and multiply it by the allowable stress, which gives us the actual allowable stress for the column. Modulus of elasticity, again, just like allowable stress, can be found for our particular species of wood in Appendix F. Okay, so I think we're now ready to look at an example problem, but I've used up a little over 11.5 of my 15 minutes, so I think I'll stop here and then we'll do an example problem in the next video.